All right. Yeah. So we can see that O is the center. We have points T, N, S, P, R, and they give us one angle, which is angle POS, which is at the center. And they tell us that there are two sides that are equal. Now, our first question is to calculate the size of angle PRS. So because we already know that we're working with angle at center is equal to twice the angle of circumference, let us see if we can kind of apply that in this question. So off the bat, we can see they're asking us to calculate this angle right there. And this is just a straightforward angle at center problem because we can see we have the angle at center, which is 60. So the angle at the circumference, which is angle PRS, is equal to half the angle at center. So it's going to be half into 60, and that's going to equal to 30 degrees. And make sure in Euclidean, when we're doing anything, we need to make sure we give our reasons. So this statement is because of angle at center is equal to 2 times the angle at the circumference, okay? So the reasons you give is just as important as the answers you are writing, because without a reason, you can't say that this is true. So you have to be able to tell them and justify why you did something, all right? So then for 9.2.2, we can see that they're asking us to find angle NST. So if we take a look at where that can be found, we can see angle NST is this angle right there. So, and again, we need to just have the whole concept of angle at center at the back of our heads. And one thing we know is that angle at center doesn't only mean that they have to be the same line, like in the first case where we had line PS. It can also be a line that is equal in length to line PS. And if we notice, line PS is also equal to line TN in length. So that means that that whole angle at center rule would still apply to this. And it also ties in with the angle subtended by equal chords theorem. So if we take a look at that, this chord is creating an angle at the circumference that we just calculated to be 30. And now a chord that is equal in length has created another angle here, which we know is going to be equal to the angle for the other chord. So what we can say simply is that angle for 9.2.2, angle NST is equal to angle PRS. And the reason for this is because equal chords subtend equal angles. And from there, all we need to do now is substitute for angle PRS, and we know that it is 30 degrees. So that is our entire problem here solved. Do you have any questions?
No.
All right. So generally in the past papers, they start off pretty simple where you have very straightforward diagrams. You don't really have to think a lot about it. You don't have to use too many steps to get your answer. But as you go on, it gets a lot more difficult, right? So we're going to take a look at an example that gets a little bit more difficult now. All right. So for this question, they tell us that D, E, F, G, and H are points on the circumference of the circle. They give us angle G1 to be x plus 20 degrees and angle H to be 2x plus 10 degrees. And another bit of information that's very helpful is the fact that ED is parallel to FG. So when you see parallel lines in your diagram, you know that you're going to probably be using corresponding angles, alternate angles, and those types of things. So for 10.1, we need to determine the size of DEG in terms of x. So we first need to identify where angle DEG is. So let's look at our diagram and we can see that DEG is the angle that is found right there. So can you tell me how we would be able to solve that angle? So there's a few things you can think about. So when you're working with Euclidean, we have an angle there. So we know that we can even think, okay, is this going to be angles in the same segment? Because that angle would equal to this angle. but I don't really know this angle at F, so I can't use that concept. But let me see what other bits of information they gave us. They gave me these parallel lines right there. And if I can take a look at my diagram, I actually have a bit of a Z forming right there, which means that angle E would be equal to this angle right there because of alternate angles, correct?
Yes.
All right. So all we really have to do from here is we identify how we're going to solve it, and we just have to write down the reason for that. So we know that for 10.1, angle DEG is going to be equal to angle G1. And that is because of alternate angles. And make sure that you give the parallel lines. And in our case, the parallel lines are ED, parallel to FG. So from there, all we need to do now is substitute for G1, which we know is X plus 20 degrees. All right, so as you can see, we identified in the problem that they gave us parallel lines, which meant that we were going to use it somewhere. And we already did in the first question. So seeing what they've given us actually helps us understand like what type of things I need to look for in my diagram. And now if I go to question 10.2, we need to calculate the size of angle DHG. So let's take a look at where angle DHG is. The angle DHG is this angle right there. So what they're actually telling us is we need to first solve for X in order to complete this problem. So if we had to look at our diagram afresh and see what we have to do, we have to find a way to calculate the value for X. Now, that's kind of difficult, but whenever you have an unknown, your primary objective needs to be to create some sort of equation to solve this. So from what we can see, we don't really have too much to work with because this angle right here is not part of a triangle. It's not subtended by a chord or something that I can easily just calculate and create an equation for. However, what we can notice in the question, they told us that all of these points are on the circumference. And what I know about when I have points on the circumference and I have lines joining these points is that if I have 4 of these points joined from the circumference, then the shape that that creates is a cyclic quadrilateral. And that's going to help me because now I have a whole bunch of different equations that I can generate, because I know for a cyclic quadrilateral, I have exterior angles being equal to the interior opposite. I have the sum of the opposite angles in a cyclic quad being equal to 180. I have a whole bunch of things. And if I look at my diagram, I can see in the previous question, I solved for this angle right here. And I know that that angle is equal to X plus 20 degrees. And it just so happens that that angle is directly opposite the angle that I'm trying to calculate. So all I have to do here is create my equation, which is going to state that angle DEG, which is the angle I calculated in the previous question, plus angle DHG, which is the angle that I actually need to calculate here, is going to be equal to 180 degrees. And the reason for this is these are the opposite angles of a cyclic quadrilateral. And now from here, I'm going to just substitute what I have these angles, even if it's in terms of X. And we're going to notice something. So angle DEG is equal to X plus 20 plus angle DHG is given as 2X plus 10. So that's equal to 180 degrees. And now if you notice, we just have an unknown for X, and we can simply solve that because we're just going to group our X's. So X plus 2X is going to equal to 3X. 20 plus 10 is going to equal to 30 degrees. And my right-hand side remains unchanged. And now from here, I'm going to take the plus 30 across. This is going to become 3x is equal to 180 minus 30. So 3x is equal to 150. And then x is equal to 150 over 3, because you're going to divide both sides by 3, and on the left, it'll just cancel out. And now when you put that in your calculator, you're going to get 50 degrees as your value for x. But remember, the question didn't ask you to just determine x. They asked you to determine angle DHG. So now what you have to do is substitute the value that you just got for x into that. So we know that DHG is equal to 2x plus 10. So all we need to do is substitute x is equal to 50. So this will be 2 into 50 plus 10. And that is going to be equal to 110 degrees. So one very key takeaway from this is they're not going to ask you to calculate something like in 10.1, they told you to calculate DEG, and they're not going to tell you to do something like that unnecessarily, right? So the first thing you need to always check is, can I link what I've already calculated to what I need to calculate? So we saw that link because in the question, we already saw that we had a cyclic quadrilateral. And it just so happened that this and the question we were doing now actually linked. So you're going to notice that happening a lot. So make sure you first look for that before you start trying to find an alternate solution, okay? All right, so.
Okay. Can you just go? Okay, fine. You can take it out.
Okay, no problem. All right, so far, are you comfortable with everything we've done? Is the pace
Yes.
okay, or is it too fast, too slow?
No, it's okay.
All
The
right.
right.
All right, so now let's take a look at something that's a little bit more difficult. Question 11. All right, so let's get into this one. They tell us that O is the center of the circle PTR, and that N is a point on chord RP such that ON is perpendicular to PR. So what you need to do is just make sure whatever information is given to you is on your diagram. So ON being perpendicular to PR. So let's just take a look. ON perpendicular to PR. They've given me the 90-degree angle there, so I don't have to worry about adding it in. They tell me that RS and PS are tangents to the circle at R and P respectively. And then they give me a bunch of different lengths and one angle. So when you see the lengths, it's probably going to be because you might have to use theorem of Pythagoras, because that's usually what's going to tie in with Euclidean and stuff like that. And now I want you to look at our diagram. We can see that in our diagram, we have a center here, and we have a chord, and I have a line from center, which is perpendicular to that chord. That rings like theorem 1 in my head, because I know that line from center perpendicular to a chord bisects that chord. So I already know that I'm going to probably be using some form of theorem 1 in this question. And I have tangents, which means that I'm probably going to be using some concept relating to tangents. So these are the theorems that need to be circulating my mind now. And if we look at the first question, they're telling us to calculate the size of angle NOR. So if we had to identify angle NOR, they're asking us to determine this angle right there. So can you tell me what that angle, or how you would approach solving this angle now? Based on all the information given to you, tell me what you're going to try and look for. So we said in the question, we have tangents and we have angle at, line from center. All right, so we can't really, I don't think we're going to use line from center for this question that much. But can you use anything linking to tangents to solve this?
Yes.
All right, so how are you going to approach it? All right, so in our question, what I want you to first see is that they've given us or told us that we have two tangents here, right? And then we also see that both of those tangents are from the same point. So tangents from the same point are equal in length. That is one of the theorems that we know. So angle RS is equal to side PS, right? So because I know this, I can kind of start solving things that I know, and maybe I'm going to get somewhere, okay? So we're going to start with that bit of information. We're going to first state that SP is equal to SR. And this is because they are both tans or tangents from the same point. And now if my sides are equal, then the corresponding angles are going to be equal, because this is actually an isosceles triangle, right? Let's just go back. Because if we look at it, we have these two sides here being equal, that one and that one, which means the base angles right here and right here are equal in magnitude. So all we need to do now is make that statement and say that the angle at P is equal to the angle at PRS, which is the angle in green at the bottom there. So now all I need to do is write out that angle PRS is equal to 42,83. So the reason that we started by looking at these sides being equal is because if you want to calculate something that's unknown, what you need to try and do is take values from where you know it and start moving it across your diagram and solving things until you reach what you actually need to calculate. So although it may not have seemed like important to first calculate this angle, we're going to see now why it actually was important for us to calculate it. So now that we know that this angle is equal, we need to make a statement or justify why we said this right here. And that is just going to be that they are the angles opposite equal sides. So you can state the sides that were equal, but we've already stated it in the previous question, so we don't really have to do that again. But now that we've established that this is an angle that we know, we'll fill it into our diagram. So I'm just going to say that this is 42, okay? But just know that it's 42,83. We're one step closer to solving our unknown, which is that angle in red right there. So let's clear everything up now, because when your diagram is messy, it's hard to see things. So all we need to do now is determine the angle at O. And now I already know the angle at R is 42,83. If I can take a look at this, I can see that angle O, although there's nothing special about it, it's within a triangle, which means that I can generate a formula to solve for angle O, because the sum of angles in a triangle is equal to 180 degrees. So if I had to write out an equation for this, I would say that the angle at O plus angle ORN, which is that angle right there in black, plus 90 degrees, because the other angle in the triangle is 90 degrees, is equal to 180 degrees. And this is because of sum of angles in a triangle. Now let's clean this up, make it a bit simpler for us to read. Angle O plus angle ORN is equal to 180 minus 90. All right, so we're one step closer, but the only thing is that we don't know angle ORN. But that's going to be our next objective now. How can we determine angle ORN? So angle ORN is actually this whole entire portion right there in purple. And there's actually something very special about that, because if we take a look at that diagram, we can see that OR is my radius. So I know that this is a radius right there. And I know that RS is a tangent. So when my radius meets my tangent at the point of contact of my tangent to the circle, that creates a 90-degree angle right there. So I already know what that huge angle is right there, because this is just going to be 90 degrees. And I've already calculated one part of this angle, which was 42,83, because we've already determined it right here. So all we would need to do to calculate the portion that's within this triangle is to say that because the angle ORS is equal to 90 degrees, because tangents are perpendicular to the radius, I can now safely say that angle ORS is basically the sum of angle PRS plus angle ORN. And all we really mean by that is it's the sum of this arc that we drew and the dots. Because if we add both of those angles, that's going to give us the entire 90 degrees. And then to solve it, we just start substituting values. We know that ORS is 90. We know that PRS is 42,83. And what we need to solve is ORN. And then it becomes simple, because to solve ORN, we take the 42,83 across, and it becomes 90 minus 42,83. And then that's simply going to be 47,17. Let me write that better. All right. Now it may look like, we're running all over the place, but now everything's going to tie together, because we needed to calculate ORN in this equation, right? So now what we're going to do is we're going to start working with this equation again by substituting angle ORN. So now what we will have is angle O plus 47,17, because that is what angle ORN is equal to 90 degrees. Because on the right-hand side, I have 180 minus 90, which is just 90 degrees. And now to calculate angle O, I need to just take this across. So that'll be 90 minus 47,17. And that's going to equal to 42,83 degrees. So if you take a look, this question is worth 5 marks. And that's why we had to do quite a bit of things in order to solve it. I did it like this to show you this step first so that you understood why we were working out angle ORM. Do you have any questions based on what we've done?
No.
All right. So when you see tangents, you need to think everything relating to tangents, because if you see in this question, we use the whole concept of tangents from the same point. So you need to keep an eye out for that. And then we also use the concept of tangents being perpendicular to the radius. So every time you see something like a tangent, that's when you know I'm definitely going to be using it. So it's important to just keep your eye out for that. So I'm going to go on to the next question. Can I clear it?
Yes.
All right. So now if we take a look at the next question, we need to calculate the length of the radius of the circle. So let's look at the question a bit closer. The radius of the circle is basically OR. So if we look at it, it's basically this line right here, because that's a radius and that's a radius, right? So we need to solve for this radius. And the way we can go about doing this is we've already established that there is a 90-degree angle here. And when I have a 90-degree angle in a triangle, the theorem of Pythagoras screams out at me. So I just need to figure out what my sides are. And to do that, what I'm going to do is just say that because I don't know what my radius is, I'm going to call my radius is equal to x. So wherever I see my radius, I'm going to assume that distance to be x, and I'm going to be solving for x in my equation. So what I will do here is I'm going to say that this distance is x, and the distance here is x. Now let me set up my whole theorem of Pythagoras equation. So the theorem of Pythagoras basically says that the side opposite your 90 degrees is your hypotenuse. And it's your hypotenuse, which is OS squared, that is equal to the sum of the square of the other two sides. So the other two sides in our case, one of them is RS. So it'll be RS squared plus the other side, which is RO. So RO squared. Now from here, I'm going to just start substituting the values. OS, I can see, is made up of a line that is length 9 and a line that is length x. So in total, OS is basically x plus 9. Because if x was equal to 5, then the whole length of this would be 9 plus 5. And that'll be 14. But I don't know what that length is, so we have it as a value of x. So that's all we had to do there. And that is going to be equal to RS squared, which we have as 15 squared, plus RO squared, which is just x squared. Now to solve this, we break our brackets, and this is going to be x squared plus 18x plus 81 is equal to 15 squared. What is 15 squared? 225 plus x squared. Now, if we start simplifying things, we can see that we'll take the 1x squared across this side, and we'll have x squared plus 18x plus 81 minus x squared is equal to 225. So x squared minus x squared cancels out. I'm left with 18x plus 81 is equal to 225. And then to simplify this, 18x is equal to 225 minus 81. And then 18x is equal to 144. X is equal to 8. So we already have established that x is our radius. So our last statement would just simply be that the radius is equal to 8 units. All right, are there any questions?
No.
Okay, so in this question, what I want you to just remember is that 90 degrees and triangles need to click that you're going to be using Pythagoras. Only if you notice that they're asking you for lengths, or if in the information they've given you certain distances, because that's all you've been taught and that's what you are probably going to be using. So yeah, that's nothing crazy right now. Can I move on to the next question?
Yes.
All right. So now let's look at the last question for 16, sorry. I'm not going to do 12.1 because that is a proof question and you can easily do that yourself. We'll look at 12.2. But let me bring 12.1 on the screen as well. Are your exams following the layout of these exams, or is it completely different?
No, it's like the past two papers.
Okay. All right. So now we can see in question 12, 12.1 was a proof, right? It was a proof that EFG, which is this angle right here, is equal to EDF, which is this angle right there. And that's just, tan chord theorem. So if they're asking you in 12.1 to prove tan chord theorem, then there's a very good chance that you're going to need to use the whole concept of tan chord theorem in order to solve the following question. So that's just what I wanted to show you with 12.1. Now that we have that at the back of our minds, let's look at what 12.2 has in store for us. For 12.2, in the diagram below, BOC is the diameter of the circle. So when I'm thinking diameter, I'm thinking that angles in the semicircle equal to 90 degrees, or the angle opposite my diameter is 90 degrees. That's something that must be in your head in case you have to use it. And then they tell us that AP is a tangent to the circle at A. So that's on our diagram. We don't have to enter anything. And then they tell us that AE is equal to EC. So if we take a look at what they've actually told us, they've told us everything. They said that this and this are equal. They told us that this line from P to A is a tangent at A. And we know that O is the center. So because we know all of these things, before we start answering our question, we can see that, okay, I have a line going from center, meeting my chord at E, bisecting that chord, which is going to probably mean that I have a 90-degree angle here and here, because that is theorem 1 that tells me that line from center bisecting the chord is at 90 degrees to that chord. Next up, they've told me that I have a tangent going from A to P, meeting my circle at A. And I know that line OA is actually a radius. So when I have a tangent meeting a radius, I have a 90-degree angle being created. So that's another bit of information that I know offhand. And then again, something else that I know is that if I have radii, that means that this side and this side are equal because my radius is constant throughout my circle. So this might help me to be able to calculate these two angles because it's basically an isosceles triangle. But before we get ahead of ourselves now, as long as we understand that these are the types of things we need to look for, let's see what the question asks of us. We need to prove that BA is parallel to OD. So BA is basically this line right there, and OD is basically this line right there. And in order to prove that a line is parallel, all you need to be able to do is to just show that the alternate angles are equal, or to show that the corresponding angles are equal, or anything that holds true when the lines are parallel. So if we can prove any one of those things to be true, then we are able to just state that those lines are indeed parallel. So let us take a look at what we would need to do here. In order for this to be parallel, we can maybe try and prove that we have alternate angles there and there being equal. But offhand, that's going to be kind of difficult because we don't exactly know anything linking those two angles just yet. So we'll put a plug on that for now. So let's see what else we would have. What would your suggestion be for this question?
I'm not too sure.
Okay. So when we are not sure, what we should start doing is just writing down things that we do know. So I said that we can solve a whole bunch of different things, right? I said that we can say that these two angles are alternate angles, or we can say that this angle and this angle are equal because of corresponding angles. And now this is the one that we are actually going to be using, because if you recall, I told you that this angle right here is 90 degrees because of theorem 1 saying that the line from center bisecting the chord acts at 90 degrees to that chord. And for the other angle, if I have a diameter right here, the angle opposite that diameter is equal to 90 degrees. And now if this is equal to 90 degrees and this is equal to 90 degrees, they are actually both corresponding angles, because if we look at our diagram, we can see that we have this F shape right there. So if these two are parallel, then this angle and this angle would be equal. And that's exactly what we proved by saying that they're 90 degrees. So all we have to do now is just put everything that I've just said in writing. So what we're trying to just say is that angle E2 is equal to 90. So let us make that statement. Angle E2 is equal to 90 degrees. And that is true because line from center to midpoint of chord. All right, so we've done one part of everything we've just spoken about. The next part that we spoke about is the huge angle right there. So we can say A2 plus A3, or we can just call it by its entire name, which is angle BAC. And that is equal to 90 degrees. Because our reason for that, you can either say it's angles in a semicircle. Make sure you write the word circle, but yeah, or you can say that it is the angle opposite the diameter. And now our last statement is just going to say, since angle E2 is equal to 90 and angle BAC equal to 90, angle E2 is equal to angle BAC. And now from this, what we can say is that, therefore, the lines BA is parallel to OD. And the reason this is true is because corresponding angles are equal. Let's get rid of the radius stuff. All right, so that's really all you have to do for 12.2.1. Were you able to follow me on that?
Yes.
Okay, awesome. All right, so just one note is that whenever you calculate something, either add it to your diagram or just be very mindful that, okay, I've already said that this is 90, so I can probably use that in another question, and even the same for E2. And because we determined or proved that the lines are parallel, what we can go ahead and do from here is we can just fill in parallel lines now on our question. And that's probably going to be something that we can use in further questions to help us. All right, so now that we know that, let's look at the 12.2.2. These are the harder type questions where you have to prove that something's a cyclic quad. So for AOCD, we need to prove that it's a cyclic quadrilateral. So let's first identify where AOCD is. We have it right here, AOCD, and we have to prove that that is a cyclic quadrilateral. So we can do this in a few different ways. We know that for something to be a cyclic quadrilateral, it needs to exhibit the properties of a cyclic quadrilateral, which means that we need to be able to prove that opposite angles are, the sum of them are equal to 180 degrees. We need to be able to prove that there is an external angle which is equal to an interior opposite angle, or we can prove that angles in the same segment, that concept actually applies in our question itself. So we can go about this a number of different ways. We just have to try and see which one is going to be applicable for our question. So we have tangents, we have parallel lines. So let's try and use that to our advantage. So we have a parallel line here and here. So knowing that this is our parallel lines, is there anything that you think you would be able to solve from here based on this? And don't worry if like you're a bit worried about it, yeah?
Opposite angles opposite angles are equal.
The sum of them equal to 180.
Yes.
Mm-hmm.
Aligned bisect.
Mm-hmm. The main ones, angles in the same segment, because then if you can prove angles in the same segment, then that means all the points are actually on the circumference of a circle, correct?
Yes.
So if we can prove that to be true, then we are good to go. So is there any way that you can think of us proving it?
I'm not too sure.
All right, no problem. So if we have to prove that angles in the same segment, that concept exists in this question, then there's only there's four things that we could possibly do. We can try and prove that this and this are equal, because those are basically subtended by this line DC. So if we can prove that A1 is equal to O1, then we'll be essentially proving that angles in the same segment exist. Or we can prove that angle A2 is equal to D2, because again, we might be able to just state that angles in the same segment exist. And let us just take a look at, what we actually have. They tell us that there's a tangent, right? So we're going to probably use this whole concept because we know that with a tangent, if I have a tangent and an angle here, that angle is equal to an angle on the inside because of tan chord. And from 12.1, I know that I need to use tan chord somewhere. So I'm going to start off by introducing the tan chord theorem into my question. So in order to write that out, I'm just going to state that A1 is equal to angle B, because A1 is up here and angle B is down here. And this is a classic tan chord case. So now that we know that angle A1 is equal to angle B, we can also see that angle B, which is that angle right there, is equal to angle O1 because of corresponding angles. So because I know that to be true, I can say also angle B, make sure you give your reason for tan chord here. Yeah, so also angle B is equal to angle O1. The reason for that is corresponding angles. And the parallel lines that we have, AB parallel OD. Okay, so we have that part done. But if we notice, we have A1, which is equal to B, and O1, which is equal to B. So we can say, therefore, angle A1 is equal to angle O1. And this is just simply a deduction from what we have. And if we look at what that basically implies, that means that angle A1, which is there, is equal to angle O1, which is there. And we already established that if we manage to prove that to be true, then we can say, therefore, AOCD is a cyclic quad. And the whole reason for this is because we just proved that it's the converse of angles in the same segment. So the whole takeaway from this is, in the first part of this question, we had to kind of prove tan chord theorem, right? So we knew that, okay, I didn't use it for 12.2.1. For 12.2.2, I couldn't really see where to start. So let me start from the tan chord theorem part and see where that takes me. And then we started noticing, okay, I can get whatever this was equal to be equal to something else. And now I equated them and I saw that, hey, those are actually angles in the same segment. And that actually proves exactly what I needed it to prove. So it's just about, trying to see the patterns in the question, trying to figure out, okay, this is where I need to go. And I need to take information from places that I have it to places that I don't, and link different things. So are you okay with this question?
Yes. Can you just like I just want to see the reason. Okay. It's fine.
All right. So I'm going to clear this and we're going to look at the last part. So we need to prove that DC is a tangent to the circle at C. So let's clear up the mess that we have and evaluate this question. So for DC to be a tangent to the circle at C, let us take a look at what would have to happen. All right, so DC is this line right here. All right, so we need to prove that that is a tangent to this particular circle. So in order to do that, we need to be able to prove something or the other, right? We need to be able to either prove that, this angle is equal to this, because that would mean that tan chord actually does exist. And if tan chord exists, then it is a tangent, because tan chord wouldn't be happening. That whole theorem wouldn't be applicable here if DC was not a tangent. Sorry, just give me 1 minute. All right, yeah, and another thing that we can actually think of doing is if we are able to prove that this angle is equal to this angle, because they both originate from D, that would make them tangents from the same point. And then you would be able to say that, you know what, it is a tangent because it's following the tangent from the same point principle. Another thing relating to tangents that we could use is this is a line, if this was a tangent, since this is a radius right here, the angle that this would make would be 90 degrees. And that actually helps us because we are working a lot with 90 degrees in this question. We've already proven that we have a 90-degree angle there, we had a 90-degree angle there. But not only do we have 90-degree angles at those 2 points, there's also a 90-degree angle here because this right there is my tangent and this right there is my radius. So I'm going to first start off with that, and then you'll see where we go from there. So angle OAP is equal to 90 degrees because our tangent is perpendicular to our radius. And the reason that this actually helps us is because in the previous question, we've proven that AOCD is a cyclic quadrilateral. So AOCD is this portion right there, which would make this angle and this angle opposite each other, right? And we've just spoken and said that if we can prove that the angle in the bottom here is 90 degrees, then we can prove the converse theorem of tangents perpendicular to the radius. So let's see if that's possible now that we've calculated one of the angles right there. So angle OAP plus angle OCD, which is this angle right there, is equal to 180 degrees. And that is because they are opposite angles in a cyclic quad. And what's left for us to do here is substitute for OAP, which is 90 plus OCD, which is equal to 180 degrees. And when we simplify, we notice that angle OCD is equal to 90 degrees. And this is exactly what we've proven, that that angle is 90 degrees. And we've already established that this is a radius right here. This is a tangent right there. And since, let's write this out. Since line DC is perpendicular to the radius, DC is a tangent. And the reason for this is the converse theorem of tangent perpendicular to radius. So that would be our entire calculation for 12.2.3. Are you okay?
Yes.
All right, awesome. So now let's take a look at the next paper, which would be 2017, okay?
Okay.
Sorry, just take some time to open up the papers and stuff.
No, it's fine.
All right, so let's take a look at question 9. All right, so for this question, we can notice that there's a proof in the first part. They're asking you to prove, I think it's theorem 1, that the line from center bisects a chord if it's perpendicular to it, right? So that proof is something you have with you, but the reason I'm showing you that that is a question here is because you're probably going to need to just know that, okay, I'm going to use the whole concept from this theorem in 9.2. Otherwise, they wouldn't have really asked me for it. So now that I know I need to just have this in the back of my head, let's see what the question actually has in store for us. So for 9.2, they say in the diagram, O is the center of circle ABD. F is a point on chord AB such that DOF is perpendicular to AB. That is on our diagram, so we don't have to worry about adding it. And then they tell us that AB is equal to FD, which is equal to 8 centimeters, and OF is equal to X centimeters. So already I can notice that this bit of information where those sides are equal to 8 isn't on my diagram. So I need to just be mindful of that. And next up, I can also see that, or remember that if I'm given units, if I'm given something in length, I need to just remember that I'm probably going to be using theorem of Pythagoras or something of that sort in order to solve this. And as we can see, we need to determine the length of the radius. And to determine the length, most likely we're going to be using theorem of Pythagoras. So let's see how we can go about solving this question. So on my question itself, I can see that I have a line from center touching this chord at 90 degrees. So the first thing I can state is that for question 9.2, AF is equal to FB. And this is because it follows the theorem 1, where line drawn from center is perpendicular to chord. So I have one bit of information, and that actually does help me because I know that the whole distance from A to B is 8 centimeters. And since I know that it's divided in half, that AF is equal to FB, I can safely say that AF, I say therefore AF is equal to 4 centimeters and FB is equal to 4 centimeters. So now if I had to redraw this diagram, it's gonna be a lot more helpful to us because now we know the actual distances in a triangle, because knowing that means I can easily set up my theorem of Pythagoras. So if we look at our diagram now, we can see that we have a distance here being 4. And we have this distance as 4. And I have the whole distance from from F to D being 8 centimeters as well. So all I really have to do now is find a way to set up a theorem of Pythagoras equation and just solve for that unknown, or solve for my radius, or solve for something. So let's do that and see where we end up. So to set up our theorem of Pythagoras equation, we know that it's going to be our hypotenuse, which is OB squared, which is equal to the sum of the square of the other two sides, which is OF squared plus FB squared. And now if I start substituting everything into my equation, I can see that I don't have anything for OB at the moment. So this is just OB squared is equal to OF, which is X squared, plus 4 squared. So in this equation, I have two unknowns. I don't know what OB is, and I don't know what X is. So my objective now is going to try and get OB in terms of X. And let's see if I can do that. OB is special because it's actually the length of, it is actually a radius, right? So if I notice, this is a radius right here, but also this right here is a radius as well. And because I know that both these lines are equal, if I can find a way to calculate line OD to determine the length of that in terms of X, then I'm going to be good to go. And let's see if we can do that. From our equation, or from our question itself, we can see that that DO, which is this distance from here to here, plus OF, which is the distance from here up there, is equal to 8, because this whole distance is FD, and it's given to us as 8 centimeters. And now that we have that set up, let's start substituting into this equation now. I don't know what DO is, because that is actually a radius. So DO plus, I know that OF is actually X. So it's DO plus X is equal to 8. And if I take the X across, DO is equal to 8 minus X. So this is going to help me, because from what I've already discussed, I know that DO is equal to BO or OB, simply because they are both radius or radii. And because of this fact, I can substitute 8 minus X in place of OB. And when I do that, I can just simply state that 8 minus X all squared is equal to X squared plus 4 squared, which is 16. And now if I want to start simplifying this, this is going to be 64 minus 16x plus x squared is equal to x squared plus 16. And this x squared and x squared will cancel, like it did in the previous year's paper that we did, which was similar to this. And 64 minus 16x is equal to 16. And then if we take this across here and this across here, what we're going to have is 64 minus 16 is equal to 16x. And 64 minus 16 is 48 is equal to 16x. And then x is equal to 3. But again, it wasn't asking us to solve for x. They asked us to determine the diameter. And we know, the radius, sorry. And we know that the equation for the radius is the one that we've established up here. So we can simply say that the radius, which is actually DO, is equal to 8 minus x, which is equal to 8 minus 3, which is equal to 5. Is that understood?
Yes. Can I just take this down quickly?
Sure, no problem.
Oh, you can take it out now.
All right, so let's move on to the next question now. All right, we'll move on to question 10. That won't take too long. So for question 10, we can see that they've given us this diagram. It doesn't look as complicated as some of the others we've seen. And they tell us M is the center of the circle, SVQR, having equal chords SV and QR, and that is indicated in my diagram. RP and QP are tangents to the circle at R and Q respectively, such that the angle it creates at the top is RPQ. So again, tangents are mentioned. So if I see the word tangents, I know I need to be thinking all of my theorems related to tangents. And in this question, I have two tangents, which would mean that I need to think tangents from the same point. So I need to know that these two lines are actually going to be equal. So if I need to use that, all I have to do is just mention that theorem of tangents from same point. So let's look at the first question. Calculate the size of angle R2. So R2 is actually this angle right here. And exactly what we just spoke about, in that whole triangle where R2 is found, we know that this and this are equal, that those two sides are actually equal, which would make R2 and Q2 equal to one another, okay? But before we get there, let's first state why those two lines are equal. So our first statement is going to be that QP is equal to RP. And this is for 10.1. And this is because they are tangents from same point. Now that I've established that, what I can now say is that therefore angle R2 is equal to angle Q2. And this is because they are angles opposite equal sides. All right, and now that we've already gotten this far, the last thing that we have to do is just notice that these two angles and the actual angle that I do know are found within the same triangle. So all that's left to really do now is to state that angle P, which is the one at the top, plus angle R2, which is the angle that we are trying to calculate, plus angle Q2 are all equal to, the sum of them are all equal to 180 degrees. And this is sum of angles in a triangle. And now our next thing that we are going to do is start substituting anything that we do know. And from my diagram, I can see that angle P is 70 degrees. I do not know what R2 is, but I'm trying to figure that out. And Q2, I know is also equal to R2. So I'm going to do that substitution so I don't have too many unknowns. And that is still equal to 180 degrees. And now we just start simplifying. So this is 70 plus 2R2 is equal to 180. We take the 70 across.
Sorry,
This is,
sorry. Why we have instead of Q2 we have R2? I didn't follow there.
Okay, on the top over here, we've done the whole thing where we said R2 is equal to Q2.
Yeah.
And because, so now instead of writing Q2, I can write R2 because I don't know what Q2 is. But if I have R2 here, that means I only have one unknown. And I can easily solve an equation that I have one unknown is compared to when I have two unknowns.
Okay, I thought as much. I just wanted to double check.
All right, no problem. It's always good to ask. So this is equal to 180 minus 70. So 2R2 is going to equal to 110 degrees, and R2 is equal to 55 degrees. All right, so that's all well and good. Now let's go and look at the next part.
I'm still taking this down quickly.
All right, no problem.
Sorry.
No, it's okay.
You can remove it.
Sure. Okay. So now that we've done that, for 10.2, we are required to calculate the size of angle Q1. So now if we see where Q1 is, it's found right there. We've calculated what R2 is, and based off our previous question, we now know that R2 and Q2 are the same. So we basically calculated angle Q2 as well. So let me first start off by writing that out. I'm just going to say that Q2 is equal to R2, which is equal to 55 degrees. All right, so we have one part of our question done, but how does Q2 link to Q1? Well, we have a tangent and we have a radius meeting that tangent, because what they told us is that M is the center. So if M is the center, a line that is coming from M to the circumference is actually a radius, right? And one thing I know about the point at which a tangent meets a radius is that they create a 90-degree angle. So what that means is that angle Q1 plus angle Q2 is equal to 90 degrees, because that's basically this angle right here. And that angle can be called Q1 plus Q2, or you can call it angle MQP. But because we are trying to calculate angle Q1, we've broken it up into its actual components. And from here, we know that Q2 is equal to 55. Okay, let's write the reason, which is tan perpendicular radius. All right, now all we have to do is simplify, because we know that Q2 is equal to 55. So we can just substitute it here and say that Q1 plus 55 is equal to 90. And Q1 is equal to 90 minus 55, which is equal to 35 degrees. So that is question 10.2 done.
You can remove it.
All right. Now, the last question here. Determine the size of angle M2. So if we had to take a look at this, angle M2 is found right there. And I kind of don't have anything within that triangle. But in the triangle that it's touching, which is this one here, I've just calculated M1. And because I know that this is a radius here, and this is a radius, because I calculated Q1, I also know what R1 is, because they both are within this triangle and they are opposite equal sides. So my first statement is going to now be that for 10.2.3, or 10.3, sorry, angle R1 is equal to angle Q1, because they are angles opposite equal sides. And from here, what I can say is that within this triangle that I have, because I know what R1 is and I know what Q1 is, using sum of angles in the triangle, I can easily determine what M1 is. So my next step is now going to be to just set up that equation, which would state that angle M1 plus angle R1 plus angle Q1 is equal to 180 degrees. And that's all within the same triangle. So my reasons just angles or sum of angles in a triangle. And now the only thing I have left to do is start substituting into this equation. From the previous question, I already know that these both are equal to 35 degrees. So all I need to do is substitute in what I know. So I know that R1 is 35 degrees. And I know that Q1 is equal to R1, which is equal to 35 degrees. So I'll write down 35, that's equal to 180 degrees. And all that's left now is just simplify everything that I have and just solve for the unknown. So M1 is equal to 180 minus 70, which is equal to 110 degrees. And now we're not done there because our unknown was M2 and not M1. But what links M2 and M1 is that they are actually equal. Angle M2 is equal to angle M1, and they are equal because they are vertically opposite angles. And our last statement is just going to be that M2 is equal to 110 degrees. And that is question 10 solved.
You can remove it.
All right, so let's move on to question 11. So for this question, again, you can see the pattern from the last paper. We had to solve, or we had to prove that something was parallel. And again, we have to prove that something is, prove that a line is parallel. So we already know what we need to just be aware of. So let's see what the question tells us. In the diagram below, O is the center of the circle. CDE is a tangent to the circle at D. DB bisects ABC, and let B1 equal to X. So let's just fill that bit of information in. They tell us that B1 is equal to X. So basically we have X right there. And they're asking us to prove that line BC is parallel to OD. So this is what we are required to prove, that the parallel lines right there do exist. So we need to kind of figure out, okay, how am I going to go about doing this? What do I need to prove? Corresponding angles, alternate angles, and co-interior angles, all of those things need to just be something we're trying to prove. And from this diagram, let's just see what we have, right? So if we are able to maybe prove corresponding angles are equal, and remember, we always work from what we know to what we don't know, then we'd be able to somehow prove that this angle right there is equal to this angle right there, because those would actually be corresponding angles and they would be equal. So let's see if we can kind of get that to be true. So we know that B1 is equal to X, right? Because that is given to us. But something else that's given to us is that B1 is equal to B2, because they tell us that DB bisects angle ABC. So the line DB bisects that whole angle right there, which means that it's split into two equal portions, which are X and X. So from this, I know that B2 is also equal to angle X. And now that I know that whole angle, my next objective is going to be to try and link it to the angle right there. And that angle is actually something kind of special to us because that is an angle at the center, and it's linked to angle B1 because they are both created by the same chord, which is called AD, or arc AD. And if I had to write out that whole thing about angle at center being twice the angle at circumference, I can easily solve for angle O1 because angle O1 is the angle at center, which is equal to twice my angle at the circumference, which is angle B1. And my reason for that is angle at center equals to 2 times angle at circumference. Right, so now that I know that, I can easily substitute for B1 and say that O1 is equal to 2x. So now because I know O1 is equal to 2x, and because I know that this whole angle right here, which is angle and angle OBC, is also equal to 2x because it's B1 plus B2. And both of them are x, so B1 plus B2 would give me 2x. Therefore, angle O1 is equal to angle OBC. And because this is true, BC is parallel to OD because we were able to prove that corresponding angles are equal. Is that okay?
Yes.
All right. And our last step here is to actually solve or show that angle C is equal to 90 degrees. So angle C is found up here, and we need to be able to prove or show that it's equal to 90 degrees, right? So what would be your plan in order to solve this?
Try to find the sum of the triangles.
All right, that is a very good start. So we need to sort of work with a triangle that C is a part of or something linking that, right? But the only thing we don't really have is that angle right there. We don't know what that angle is, and we need to figure that out. So let's start working towards figuring that out. So in order to figure this angle out, I need to just be mindful that CD is a tangent, right? Which means that because it's meeting this radius here, this whole angle that's created is 90 degrees. So if I am somehow able to calculate this angle D1, then I can subtract that from 90 and get my angle D2. So let's try and do that and calculate D1 and see if we end up anywhere useful. So in order to calculate D1, that actually looks very simple because OB is equal to OD. And that's because they are both radii. And because they are both radii, then I know that D1 is equal to angle B1 because they are angles opposite equal sides. And now because that's true, I can easily state that D1 is equal to X. And now I already told you that angle D1 plus D2 is equal to 90 degrees. And that is because the tangent is perpendicular to the radius. And so if I know this to be true, I can substitute for D1 and say that it's X plus D2, which is equal to 90. And I want to calculate D2, so I know that D2 is equal to 90 minus X. So now that I've gotten to this point, let's start looking at angles within a triangle. So if we do that, we can see that I have X here. Oh, sorry, I have 90 minus X at D2. So it'll be D2 plus B2 plus C, which is equal to 180 degrees. The reason is sum of angles in triangle. And from there, all I need to do is start substituting for everything. And I know that D2 is 90 minus X. I know that B2 is X and my unknown is C. And now what I need to actually do is start simplifying this. So minus X plus X actually cancel each other out. And I have 90 plus C is equal to 180. And then C is equal to 180 minus 90, which is equal to 90. And that's exactly what we needed to prove in the question.
Oh, I'm done.
All right, so let's look at our last question, which is question 12. It looks like a very messy diagram, but I think it shouldn't take us too long to get through. All right, so this is really what we have to do. We can see for 12.1, we need to name with reasons 4 angles equal to x. And our diagram looks very huge. They tell us in the diagram below, 2 circles touch each other externally at point P. So we can see that point P is found down there. And QPR is a common tangent to both circles at P, and EDRC is a tangent to circle BPFC at point C. There's a whole bunch of jargon there, but everything's on our diagram. And they give us angle Y and angle X. And then they give us a set of parallel sides. So using all of that information, we need to find a way to name 4 other angles equal to X. So let's look at our diagram and find where X is and if we can find anything else equal to X. So X is found right here. So for 12.1, we need to find 4 other things equal to X. And straight away, that is a little bit simple to do because we can see that this angle here is also equal to X because they're both from the same chord down here. And that just means that angle E is equal to angle X because they are angles in the same segment. So I have one part down already. So I'm just going to note that this is X. Now let's look at another one. I have tangents as well, and that's going to kind of help me. Let me see if I can use that to my advantage. We can see that we have angle P1 right here, which is this angle right there. And that angle is actually forming with this chord right there. And since this is a tangent, we can apply tan chord theorem and say that angle P1 is equal to the interior opposite angle, which is angle X. And the reason for that is tan chord theorem. So we have 2 down, we have 2 to go. So if we had to identify anything else equal to that, we can notice that P1 and P5 are vertically opposite. So we know that P1 is equal to P5, and that's equal to X. The reason for that is they are vertically opposite angles. And lastly, we can see that if we had to use these parallel lines right there, X is going to equal to C2, or rather angle C2 is equal to X. And that's simply because alternate angles and our parallel lines that we have to name are AD parallel to BC. So that's the first question done. Any questions?
No.
All right, let's close this up. 12.2. Show that EPA is equal to X plus Y. So let's identify where EPA is. EPA is actually angle P7. So we need to find a way to prove that that is equal to X plus Y. So do you have any idea as to what we can do? I know the diagram is messy, and if you can't see it even, that's completely fine.
I can't see it.
All right. So because they're telling us we need to show that something is equal to x plus y, we first need to find where y is. So we can see that y is found right here. And if I look at this big angle right here, that angle is actually equal to x plus y, because that angle is basically C1 plus C2, which is equal to x plus y. So we can just call this angle DCB, and that's equal to x plus y. So we have somewhere to start off. Now let's see if we can transfer this to another angle. Using the parallel lines, we can see that this angle is equal to this angle, purely because they are corresponding angles. So because I know that, let's just put it in, see if that helps us at all. So angle DCB is equal to angle D1, which is equal to x plus y. And the reasons for that is corresponding angles. And just make sure you put in the lines that are parallel, right? And because we know that D1 is equal to x plus y, let's see if we can get D1 equal to anything else. We know we need to solve for P7. And if we actually look at it, P7 and D1 are actually angles in the same segment because they are subtended from this line AE, or that arc AE. And they are creating both of these angles at the circumference. So if we write that out, all we have to say is that P7 is equal to D1, which is equal to x plus y, angles in same segment. And literally, this is what we needed to prove, because EPA is the same thing as P7, which is x plus y. It's just another way of writing EPA. All right, so the last question. Can I do the 12.3?
Yes.
All right. So we'll go through it.
I gotta put a lost over here, but I'll just watch it again since you said you're uploading the video.
Sure. We can discuss it. Okay, so which point did you get lost at?
Where you said corresponding angles.
All right. So if we look at this,
can you explain that part too?
yeah, the corresponding angles part.
Yeah.
Yeah. So if we look at this angle here and this angle here, those are both corresponding angles because of this parallel line here and this parallel line here, because this actually forms an F. Can you see that?
Yes, now I can.
So that's where we get the whole concept of using corresponding angles.
Okay.
And then do you know how we got angles in the same segment?
No, can you just explain that too?
Sure. So if we look at a circle like this, and we have a line here, and there's an angle being created up here and an angle being created up there, right? So we know straightforward that this and this are angles in the same segment, correct?
Yes.
But we can also look at it another way, because if I have an imaginary chord here, just joining those 2 points, then this chord is creating an angle up here and an angle up here, correct?
Yeah.
So then this means that both of these purple angles would be equal as well. So similarly, in our diagram, we have this chord that's not really drawn, but it exists, and it creates an angle up at P7, and it also creates an angle down here to D1. So that's how we kind of linked P7 to D1 and said that they are both angles in the same segment. It doesn't
Okay,
make...
now yes,
Okay.
it does make sense.
All right, awesome. So the last thing here now is to determine the numerical value of x plus y if it is given that DCTP is acyclic quadrilateral. So I'm going to first put a new page. All right. So they're asking us to determine what x plus y is if it's given that DCTP is acyclic quadrilateral. So let's first try and see where DCTP is. So if we look at it here, DCTP is actually the shape that is created right here. So they're telling us that this is a cyclic quadrilateral. We don't have to prove anything relating to that. All we need to do now is solve for x plus y. And one thing we know is that this angle, this whole angle right here is x plus y, because we've already mentioned it right there. So because we know that's x plus y, we know that, this is probably my starting point. And what I need to try and do is see if I can solve anything else within this question. So if we take a look at this, we can see that we've already gotten P1 in the first question, and we said P1 was equal to X. So we know what P1 is. So I'm just going to state that even though we've already done it, just so we have it all together. And yeah, so 12.3, P1 is equal to X. Now I also need to know what P2 is and what P3 is. P3 is going to be kind of easy to get because if we look at the previous question, we determined what that angle is. Am I right?
Yes.
And that angle is equal to P3 because they are both vertically opposite one another. So now P3 is also equal to X plus Y. And the last thing that I do need is I need to find a way to get angle P2. So the way we get angle P2 is, okay, why don't you tell me what you think about P2? Think tangents. That's the one hint I'm going to give you. Because I know that there's a tangent going in this direction, and there's a tangent going in this direction here. And tangents from the same point, what does that mean?
Tangent perpendicular radius.
No,
equals...
tangents from the same points are equal.
Oh, yes.
So that it would mean that that's the case, which would mean that the base angles are equal, which would mean this angle would equal to this angle, correct?
Yes.
So because I know that, P2 is actually going to equal to C1, which is equal to Y. So now I have all the angles up here that I needed to calculate. And I already know all the angles down here because I know that this is X plus Y. So one thing I know is that they've already told me that this purple shape is acyclic quadrilateral. That means that I can use everything linking the angles within the cyclic quadrilateral. And what links both of these is opposite angles in a cyclic quadrilateral. So that would mean that the whole top portion, which is P1 plus P2 plus P3, plus the whole bottom portion, which is simply X plus Y, is equal to 180 degrees. Because the reason for that is opposite angles in a cyclic quad. And now all that's left for me to do is start substituting everything that I know. I know that P1 is X. I know that P2 is Y. I know that P3 is X plus Y. I know that this right here is just simply X plus Y, and that's equal to 180 degrees. Now let me group everything that I have. I have X plus X plus X, which is 3X, plus Y plus Y plus Y is 3Y is equal to 180 degrees. Now, I want to just divide throughout by 3 because I want to get only X plus Y on its own. And when we do that, these 3's cancel, these cancel, and what I'm left with is X plus Y is equal to 180 over 3, which is simply 60 degrees. And what we needed to calculate was a numerical value for X plus Y, and that's what we achieved. Do you have any questions about this one?
No, it was a tricky one, but
It was. But one thing I want you to know is that if they give you information, like they tell you that this is a cyclic quad, most likely you're going to have to try and use something linking to that. And I'm sure you noticed that in a lot of these questions, when you're using cyclic quadrilaterals, you're going to be using the concept of opposite angles in a cyclic quad, because we've done that in the past, the last year's paper as well. So yeah, just keep that at the back of your mind. All right, so are you ready to move on to 2018?
Yeah.
Okay, awesome. So let's see how far we can get in that paper. All right, so we'll start off with this question 9.1. In the figure, O is the center of the circle. A, B, C, D, and E lie on the circle such that chord AB and DC are equal in length, and we're given an angle AEB, which is equal to 39 degrees. 9.1.1, determine the size of angle O1. Generally, in the first few questions, we're going to just be using one or two theorems. And what we can see is that we have an angle at center, angle at circumference, equal chords, exactly the same setup as 2017, which is kind of going to mean we're going to use just angle at center formula and angle subtended by equal chords theorem as well. So for 9.1.1, determine the size of O1, and very straightforward, O1 and angle E are linked because O1 is the angle at center and angle E is the angle at circumference. So for 9.1.1, all we really have to do is say that O1 is equal to twice the angle at circumference, which is 2 into 39 degrees. And the reason for that is angle at center is equal to 2 times angle at circumference. And we just have to simplify this, and we are going to get 78 degrees. So now that we've gotten 9.1.1, that did not take long. And to do 9.2.2, 9.1.2, sorry. we have to determine the size of O2. And in order to do that, we can just see that O1 is subtended by chord AB, and that chord is also equal to chord DC. So that would mean that angle O2 is equal to angle O1, simply because equal chords subtend equal angles. And then O2 is equal to 78 degrees. So that's this part done. Any questions?
No.
All right, let's look at the next question now. For 9.2, they've given us a diagram with S as the center. They've told us that PT is the diameter and RST is equal to X minus 8 and PQR is equal to 2X minus 40. Determine the value of X. So this is kind of a trick question because if you notice, the whole theme is angle at center, right? From the previous question, it was angle at center. And again, we can see this is kind of a different version of angle at center, because if we remember from our notes or theorems, angle at center can work when we have an angle at the center and an angle at the circumference, but it can also work in a different way. It can work if we have a shape that looks something like this. But what this would mean is that my angle at center that I would refer to now is actually the outer angle and not the inner angle. And it's this outer angle, which we can call angle A, and we'll call this B, which is equal to 2 times the angle at the circumference, which is this angle, which we would call angle B. So using this whole concept right here, we're going to solve this problem right there. So it's just a different play on angle at center. So just, yeah, be very cautious of which angle you're using. So in order to solve this now, what we would need to do is be able to figure out what that whole angle would be on the outside. And in order to determine that, it's simply just going to be whatever this angle was right here, plus 180 degrees, because a straight line is just 180 degrees. So that's just going to be 180 degrees plus X minus 8, because that's what's going to give me my entire outer angle right here. You with me so far?
Yes.
Right, now that we have that outer angle, all we have to do is apply the whole rule that we know that I've just showed you to say that that outer angle is equal to 2 into the angle at the circumference, which in our case is 2x minus 40.
Sorry, why is we have 180 plus?
All right, so we needed to determine what this whole angle out here was.
Oh.
So we know that this portion is given to us as x minus 8. But what we needed to also figure out was what this portion is equal to. But we know that this is a straight line, so that's equal to 180 degrees. So the whole thing would be 180 degrees plus whatever this was, which was x minus 8. You get it?
Yes.
All right, so once we've got that figured out, we say that it's equal to the angle, is equal to 2 times the angle at the circumference. The angle at the circumference is that angle right there. So it's equal to double that angle. And now all we do is we start simplifying it. This is 180 plus x minus 8, which is equal to 4x minus 80. And if we start simplifying everything from here, I'm going to take the minus 80 across and the plus x across. So what this is going to give me is 180 plus 80 minus 8 which is equal to 4x minus x. And then when we start simplifying, this is going to become 252 is equal to 3x, and x is equal to 84 degrees. So we also need to make sure we give our reason, and the reason for this is just angle at center is equal to 2 times angle at circumference. All
I'm
right,
done.
perfect. Now let's look at the next part. So the next question, let's delete the top question. In the diagram, always the center, chord AC is perpendicular to the radius at B, and OB is equal to 2x units and AC is equal to 8x units. Show that the length of BD is 2x into root 5 minus 1 units. Now, this is a very straightforward theorem 1 question where we have line from center drawn perpendicular to the chord bisects the chord. So for 9.3, what we need to just make sure we state is that AB is equal to BC. That's the most important thing for us right now, because that's really one thing we know based on the theorem, and that's just the whole reason line from center perpendicular to chord. All right, so now that we've established that, we can start filling in whatever information we have. They tell us that OB is equal to 2x units, so we'll fill that in. They also tell us that AC is equal to 8x, which means that each portion is equal to 4x, because we already know that AC is split in half. And that's really the only bits of information that we have. And let's see, they tell us perpendicular, they tell us there's a radius. All right, awesome. So now that we have this bit of information, when we are working with length, theorem of Pythagoras straight away. So we're going to set up a theorem of Pythagoras equation for the triangle on the right hand side, because that's where I have the most information, or even the left, but we'll just start at the right, okay? So if we're working with the right hand side, my theorem of Pythagoras equation is going to be OC squared is equal to OB squared plus BC squared. And if I start substituting what I know that OC squared is equal to, OB is given to me as 2x. BC is given to me as 4x. So OC squared is equal to 4x squared plus 16x squared. And OC squared is equal to 20x squared. And if I wanted to find OC, it's equal to the square root of 20x squared, which is equal to 2 root 5x. Okay, now that I know what OC is, I can see that OC is equal to OD because they're both radii. OD is equal to OC because they are both radii. And because of that fact, I can say that OD is equal to 2 root 5x. But the question wants me to figure out what BD is. And I can see that on line OD, I do have BD there, because OD is equal to the sum of OB plus BD, because that's the two components of my line. And now if I start substituting what I do know, I know that OD is equal to 2 root 5x, and that's equal to OB, which is 2x plus BD. And now I'm trying to solve for BD. So I'm going to take the 2x across. So BD is going to equal to 2 root 5x minus 2x. And I can pull out 2x as a common factor. So this is simply going to be, well, let's see what they want us to be. Yeah. So 2x into, if I divide the first term by 2x, I'll only be left with root 5. Minus, if I divide the second term by 2x, all I'm left with is 1. And that is exactly what they wanted us to prove it to be. Make sure you write the word units at the end. Okay.
Yes.
Perfect. Now let's move on to the next question. All right, so I'm just going to quickly show you 10.1, even though it's a proof question. So for 10.1, you can see that they're asking you to prove that opposite angles in a cyclic quadrilateral are supplementary, or the sum of them is equal to 180 degrees. So knowing that this is what they're asking you in 10.1, that means that in 10.2, most likely you're going to be using some concept relating to that. So let's look at what 10.2 is asking of us and just try and solve things from there and see where it goes. So for 10.2, they tell us in the figure QS and PR are diameters of the circle with center O such that PQ is parallel to SR. That's all given on our diagram. And they tell us PS is produced to T, N is a point on the circle such that Q1 is equal to Q2. So that's a very important bit of information. Q1 is equal to Q2. And SN is drawn. They tell us that S1 is equal to 4x. It's equal to 48, sorry. And then that's on our diagram. So for 10.2.1, determine with reasons the size of Q1. So in order to do that, we have to just see where Q1 is. So we already know Q1 can be found right here. And when we're working with Euclidean, we need to take information or values from places we know to places we don't. So we have an angle up here that we do know. And the way it actually links to this is that it is the exterior or external angle of a cyclic quad. And so if we had to write that out, we would say that S1 is equal to Q1 plus Q2, because that's what this angle is made of, Q1 and Q2. And we know that S1 is equal to 48. So 48 degrees is equal to Q1 plus Q2. But also Q1 is equal to Q2 because that's what they've told us in the question itself. So where I see Q2, I can actually write Q1. So now I will say 48 is equal to Q1 plus Q1. 48 is equal to 2Q1. And then Q1 is equal to 24 degrees. So we've managed to solve the first question. Second question, we need to solve for angle R. Angle R is found right here, and it actually links to Q1 because they are both angles in the same segment. So this was A. For B, angle R is equal to angle Q1. Reason is angles in same segment. And that's just simply 24 degrees. And then our last thing that we have to really look for is angle M1. And if we take a look at where angle M1 is, it's found right there. And we need to find a way to solve for M1, but that again is quite simple because M1 is that angle right there, and it's touching this parallel line. And again, at the bottom, I have a corresponding angle, which is Q1 plus Q2. It creates corresponding angles. And so all I have to do is just say that M1 is equal to angle Q1 plus Q2, simply because they are corresponding angles. And therefore it's equal to 24 plus 24, because we've already proven that Q1 is 24 and Q2 is equal to Q1. So that's equal to 48 degrees. And lastly, for 10.2.2, we need to prove that ST is a tangent to the circle passing through M, N, and S. So ST is this line right from there to there. And they're telling me I need to prove that that is a tangent to a circle that would be around M, N, and S. So there needs to exist some imaginary circle that touches all these points right here. And so when working with tangents, if I want to prove something's a tangent, I need to prove that any proof relating or any theorem relating to tangents exists. And in this case, that would mean that this angle that's created by my tangent and a chord needs to be equal to this angle right here, because that is tan chord theorem. And oddly enough, we already know that S1 is equal to 48 degrees and M1 is also equal to 48 degrees. And those are both the angles we said we needed to be equal. So since M1 is equal to S1, ST is a tangent simply because it's the whole converse tan chord theorem. All right.
Yes.
All right, so then let's quickly just do question 11, and then we can call it for today.
Okay.
All right, question 11. So we need to prove that PR bisects angle ORN. The information given to us is that O is the center of the larger circle, RTAP. OP is the diameter of the smaller circle, PSO, and NP is a tangent to both circles at P. RN is perpendicular to NP, and that bit of information is given to us, so we are all good. Oh, so this question actually does have a small error in it. They're supposed to tell you that these two lengths are actually equal. So yeah, just make that small adjustment. So now that we know all of these things to be true, we need to prove that PR bisects angle ORN. So let's first try and see where PR is. PR is the line right here. And ORN is actually this big angle right there. So what we are actually required to prove is that R1 is equal to R2. Because if we prove that, then we can prove that that big angle is actually bisects it, because it's in two equal halves. So the way we would go about doing this is we'll try and calculate one angle or the other. But they give us a starting point and they tell us that we must let P1 equal to X. And in Euclidean, we always start from where we know something and move to where we don't know anything. So let's see what we can equate P1 to and see where we go from there. So from our diagram, we can see that angle P1 is equal to angle T1, which can be found up here because of tan chord theorem. So P1 is equal to T1, which is equal to X, and that's simply because of tan chord theorem. Next up, if I can equate anything to X, yes, I can. I can see that this angle T1 and this angle O1 are linked because O1 is the angle at center and T1 is the angle at circumference. So O1 is equal to 2 times the angle at the circumference, which is T1. This is angle at center is equal to 2 times angle at circumference. So that's equal to 2x because I know that T1 is equal to x. All right, so can we move anywhere else from this? Yes, we can, because now that we know what O1 is, we brought it into this triangle where R2 is. And that's kind of what I needed because I need to calculate R2 or try and figure out something about R2. And I can see that this line and this line are actually equal because they are both radii. So I'm going to state that OR is equal to OP. The reason for that being that they are radii. And then from there, I can do a whole sum of angles in the triangle, which would state that O1 plus R2 plus P2 is equal to 180 degrees. And I'll start substituting for what I know. I already said that R2 is going to equal to P2 because the opposite sides are equal. So angle R2 is equal to angle P2 because they are angles opposite equal sides. So therefore, your new equation is now O1 plus R2 plus R2 is equal to 180 degrees. And I already know O1 is 2x. So 2x plus 2R2 is equal to 180 degrees. And then 2R2 is equal to 180 minus 2x. And then angle R2 is equal to 90 minus x. So we now know what angle R2 is, which is 1/2 of what we need. But now let's see if we can calculate R1. So looking at the triangle at the bottom left, we can see that we have everything we need to calculate angle R1. Because if we do sum of angles in that triangle, it would be angle R1 plus angle M plus angle P1, which would equal to 180 degrees. Again, sum of angles in triangle. And now if we start substituting what we know, this would be R1 plus 90 plus x is equal to 180. And then R1 is equal to 180 minus 90 minus x, which is just 90 minus x. And now if we take a look at what we've calculated, we can see R1 is 90 minus x, R2 is 90 minus x, therefore R1 is equal to R2, and therefore PR bisects ORM. I know that was a lot, and I'm sorry if you did get lost anywhere, and I hope maybe the recording would help you follow along a bit better. But are you okay for this question?
Yes, I understood it.
Okay, perfect. So the last question now, let's clear everything out, is simply going to be to prove that angle ROS is equal to angle PAT. So let's first try and see where our angles are. Angle ROS is this angle right there. And they're asking us to prove that it's equal to angle PAT. And PAT is this angle right there. All right. So we need to kind of figure out a way to solve this question. So let's see what we can actually figure out first. So we only have two things we're going to be working with, ROS, which is equal to PAT. So we can choose either to start trying to figure out the left or the right-hand side. So let's see what we do know. I told you that the missing information is that these two are actually equal to one another, which means that I have a line from center going to my chord, bisecting the chord, which means that angle S2 is equal to 90 degrees because of the whole line from center. You can just fill out the rest of this theorem itself. So because we know that S2 is equal to 90 degrees, what else can we figure out from there?
Opposite.
So think triangles. So look at angle ROS.
Yes.
So our angle ROS is that angle right there. So is there any way that we can link what we've just found to that angle right there?
Opposite angle?
No, because you see, S2 is actually this angle right there. So we know that R2, which is this angle right there, is actually equal to 90 minus X. All right. So we know that bit of information. And let's see if we are able to calculate anything at all, right? So in this diagram itself, before we move on to this, let's look at angle PAT, which is this angle right here. These two are actually opposite angles in a cyclic quadrilateral. So angle PAT would be equal to 180 degrees minus 90 minus X. Because of opposite angles in a cyclic quad. And now if we simplify this, this is going to be equal to 180 minus 90 minus plus X, which is equal to 90 plus X. So we now know what angle PAT is, which is half of our problem solved. The only other thing that we really need to calculate now is angle ROS. And angle ROS can actually be found right here. And one thing we do know is that at 01, our angle that we calculated was 2x. So the only thing that we really had to do was to solve for Q2, correct?
Yes.
All right. So how would you go about solving angle Q2?
Q2.
O2, sorry.
O2.
All right, so this is what you can actually do, right? We've already established that S2 is equal to 90. So if you don't want to calculate O2, what you can instead do is to figure out this angle right here. That is actually an external angle to this triangle, correct? This would be an external angle, which would mean that it's the sum of this angle and this angle. So I'll just set up that equation and say that angle ROS is equal to angle S2 plus angle T1. And we've already just calculated that S2 is equal to 90 degrees. And we've already determined that angle T1 is equal to X. Now, if we see PAT is equal to 90 plus X, ROS is equal to 90 plus X. So angle PAT plus ROS is equal to 90 plus, not plus, sorry. PAT is equal to ROS, which is equal to 90 plus X. And that's literally what we needed to prove. So do you have any questions now about this?
No.
All right. So yeah, I hope the lesson was helpful.
Yes, it was.
All right. Yeah, that's great. If you do need any other or further help, let me know, because I know we didn't cover 2019 and 2020, but yeah, I think you should be fine.
Yeah, I'll do it, and like anything I need help with.